little window for people to show up. Sean, can you hit record?
We are.
Hi, everybody, and welcome to the Pony Virtual Users Group for September 1st, 2016. Today we have Andy Turley giving a presentation on garbage collection in Pony called The Art of Forgetting. Take it away, Andy.
All right. Thank you, Sylvan. And thank you, Sean, for letting me talk here today. So like Sylvan said, my name is Andrew Turley, and I'm going to be talking about garbage collection in Pony. So the first thing to know is that Pony automatically collects your garbage. It's a garbage collected language, and garbage is anything that your program created but no longer needs. So when garbage is collected, the area of memory that it occupied is freed and can be used for new things. So when you've got a program that's running, you're constantly creating new objects, and in languages like C, you have to explicitly free those things when you're done using them. Pony keeps an eye on your system and determines when objects are no longer being used, and it recycles that space so that it can be used by new objects that are created. And that way you can pretend like you have infinite memory when you really only have near infinite memory. So I want to talk a little bit about some garbage collection background. There are two different approaches to dealing with garbage collection, sort of. There should be a little asterisk there. But there are two major ones, and they are reference counting and tracing. So with reference counting, objects keep track of how many other objects refer to them. So I've got a little diagram over here that is what you would get if you, in some programming language, had an object called B that had a next, and you assign that to C, and then C has a next, and you assign that to D. And so B has a reference coming from the root of your program, or some sort of root. C has a reference from B, and D has a reference from C. So they all have a count of 1. In this next step, we set C next to null, or whatever it is in your language, so that now there is nothing that actually refers to D. So D's count drops to 0. And once that happens, it's garbage, and it can be collected. Now, with reference counting, one of the things you have to watch out for is cycles. You need to have a way of dealing with that. So in this example, I have 2 D's, but that bottom D should actually be an E. But you can see that B has one thing referencing it, the root. C has 2 things referencing it, D and the other D. And each of the D's only has 1 thing referencing it. So in the next step, we say that B next is null. So what that does is it isolates this cycle of objects here, the C, D, and other D. And so it's kind of off floating in its own area. So even though there's nothing connecting it to the main part of the program, each of those objects still has a reference count of 1. There are a number of different ways of dealing with this, and I don't want to get into that too much right now, but that's kind of the big trick when you're doing reference counting, is how do you deal with cycles? So the other approach is tracing, and how tracing works is that every so often you start with some known root objects and figure out which other objects can be reached from those roots. Any objects that are not reachable from the roots are garbage and can be collected. So there's a few questions that come up when you deal with a strategy like tracing. One is, when do you actually stop and do this? You don't do it all the time after each modification. That would be too slow. You want to kind of defer it. So how long do you wait? And the amount of time that you wait kind of determines how much time you spend in garbage collection. So there's some latency considerations that come up there. You're basically trading some throughput for some latency, depending on how long you wait. Another question is, what are your roots? So different tracing algorithms have different ways of saying, okay, this is the object that I'm going to start with that I know is alive, and then I'm going to trace from there and figure out which other objects I can reach. And then anything that's unreachable is dead. You can perform certain optimizations by selecting your roots in different ways and only searching over those roots at different times. The final thing is that you have to stop everything to avoid mutating the graph if you have multiple threads that are acting on the graph. So basically, like I said, with tracing, every so often you start with the known objects and you work your way through. So again, we have this list of objects here that are all kind of pointing to each other. And we modify it so that B no longer points to C. So again, we have this disconnected cycle here. But now instead of looking at the cycle, at the count of how many references each object has to itself, or coming into it, we start with the root, and we say, okay, we know we can reach the root. What can we reach from the root? Well, we know that we can get to B, so B must still be alive. Everything else couldn't be reached from the root, and so we assume that it's garbage, and we collect it. So again, like I said, you need to stop all of your threads if you have other threads that can possibly be mutating this actor graph. Because what could happen is that while one thread is tracing and looking to see how objects are connected, another thread could have changed the graph, and so suddenly things that were connected are no longer connected, or things that weren't connected now are connected. So when you hear about Java and people talk about, oh, stop the world garbage collection, that's what they're talking about. They're stopping the entire program, or all the user threads in the program, and then they go through with a garbage collection thread and look at each of the objects and see how they're connected to each other. So I said that there were two approaches. Really, in most systems that you'll find in the real world, they use some form of a hybrid approach to garbage collection, which involves both tracing and reference counting. And that's a quote from this a unified theory of garbage collection paper, which is really good if you're interested in garbage collection theory. And it is accurate in the case of Pony, which we'll get to in a little bit here. So I'm going to go into some Pony basics here so that anyone who doesn't have a lot of experience with Pony kind of comes to this with the level of understanding that they need. So if you already know this, I apologize for repeating things that you already know. Pony is an actor-based object-oriented language. You have objects which respond synchronously to function calls, and you have actors which respond asynchronously to messages. Objects store state and provide functions for acting on that state. Objects in Pony are pretty much like objects in most other object-oriented languages. I'll just point out that in Pony, there's a distinction. Method means something a little different than functions, but functions, as we talk about them in Pony, really are what you would think of as methods in other object-oriented programming languages. So I've got a little example here. We have an actor called main, and we have two classes that it uses. We have one called example and one called other. So don't worry too much exactly about what an actor is right now if you don't know. We'll get to that in a minute. But pay attention to the flow of the program here. So what main does is it creates an example object, and it creates an other object, and then it calls the foo function of example twice with the other object. And so if you take a look at example, what example does is it gets initialized in that create function with a string. It stores that string, and then every time foo is called, it reverses the string and then sends that reversed string to say. It makes a call to say in the other object. And if you look at the other object, we're initializing that in the create function with env, which in Pony is the environment, and I'm using it here to print things out. So here's kind of the life cycle of this little program that we've written here. That little starry box there is the runtime. And the first thing the runtime does is it creates a main object, and it sends it a create message. So when main starts handling the create message, the first thing it does is it instantiates that example object and passes it howdy as its text. Then it goes, and the next thing it does is it instantiates an other object, and it passes env to that. After that, it calls foo, and foo calls rev. Rev reverses the text. And now that it gets the return value from that, it calls say, and it prints out yidao, yidwo, howdy backwards. And then main calls foo again, foo calls rev again, rev reverses the text again, so now it turns back into howdy. And then we call say again on O, and now O prints out howdy, frontwards. So the thing to keep in mind here is that when you make a function call, that blocks. And so in this last call here, main is waiting for foo to do something, and then foo is waiting for say to complete. So this is all this is taking place all in the same thread of execution, and it's all, the different pieces are waiting on each other. So actors are a little different than objects. Actors also store state, and they act on that state, but they do it in response to messages. So here's the life of an actor. An actor has a queue. The queue has 0 or more messages in it, and the actor gets the next message in the queue, processes that message, and then it collects garbage. And while it's processing messages, it may send messages to other actors. It'll probably call a few functions. It'll interact with the objects that it knows about. And that's how it gets work done. So here's an example of something that, of 2 actors. And we've got an actor, Donald, and it has behaviors called foo and bar. And again, behaviors are the things that process the messages. So that means that Donald can receive a message called foo with no arguments, or it can receive a message called bar with some sort of arguments. And then we have an actor called Jessica, which creates a Donald actor and then a something object of some sort. And when it receives a Baz message, it sends the message foo to Donald, and it sends the message bar to Donald. So actors can be run in parallel. Actors are asynchronous, and so they're kind of executing on their own behalf. So the way that this is implemented in Pony, by default, you'll have one thread that gets started for each CPU that you have. And then those threads will execute one behavior at a time on behalf of an actor. And so as you can see, we've got A1 bar running consecutively with A3D, which runs consecutively with A5 mu and A8 phi. And then these things can kind of run at their own pace. Actors are assigned to a thread, so they have kind of a home thread. But if a particular thread doesn't have anything to do, it can see if there's any more work to be done and do that work on behalf of another thread. So one thing to keep in mind is that behaviors cannot be preempted. So if you look here, we can't run part of A2 Baz and then run A1 bar in the middle of it and then continue with the rest of A2 Baz. That particular thread can only run a behavior from start to finish. Again, you can have other threads that are running other behaviors at the same time on other actors, but you can't have a behavior execution split apart. The other thing that you're not going to have is the same actor running in 2 threads. Actors are unit of concurrency in Pony, and they're essentially single-threaded. So you're only an actor is only handling one message at a time. So here's an actor example, and you'll notice it looks a lot like the object example, but now instead of having classes, we have actors. So it starts out the same way. We create a main actor, and the runtime passes it a create message. And so the actor handles create. So the first thing it does is it creates an example actor. Now, if you look here, we've got create, and create is, oh shoot, sorry. So create is a constructor, but in this case, in the case of actors, constructors are behaviors. So Pony creates that, or instantiates this example actor, and then it sends it the create message. And then the next thing main does is it instantiates the other actor, and it sends that a create message. Now, in this next slide, what's happened is, remember, main is still running on its own, and now the other actors start running on their own as well. So main now sends a foo message to the example actor. Meanwhile, the example actor has started processing the create message that it received, and it sets its text to howdy. And the other object has also started processing its create message, and it sets its underscore environment variable to env. Now, now foo is going to send another message to the example object, and this is the next foo message that it needs to get. So now the example object gets the next message that it needs to process, and it starts processing it. So it sees that it's got a foo message. It calls the foo behavior. Foo calls rev. Rev reverses the text. And now, again, within that foo behavior, it sends a message to the other object, and it sends the same message. Now, the other object starts processing the same message, and at the same time, the example object starts processing the next message in its queue. And so again, it processes that, it reverses the text, and then it sends another message to the other actor. So now the other actor processes that next message, which is say howdy, and it prints out howdy forward rather than reversed. So the thing to keep in mind, a few things to keep in mind here. One, notice that the example actor has both behaviors, a behavior and a function. It has a behavior called foo and a function called rev. Also, notice that at this point, at the end of the program, main hasn't had any work to do in a while. So the main actor was done with its work, but the program is still running because there are other actors that have messages in their queues that are processing those messages. So the program doesn't stop running until all of the actors have finished processing all of their messages. So one thing that Pony has that we'll talk about in a little bit when we talk about some of the garbage collection things that involve messages is there's causal ordering. And that means that messages arrive before any messages they may have caused if they have the same destination. So that'll become kind of important when we talk about when things happen and which messages get processed when. The other thing that Pony has that has an impact on garbage collection is reference capabilities. So Pony uses reference capabilities to control how references to an object can read and modify it. So there's a couple of rules that are basically enforced by reference capabilities. And one is that if an actor can read an object, then no other actor can modify that object. And if an actor can modify an object, then no other actor can read or modify it. So this is a little different than how most other languages deal with concurrency. There are languages like Erlang which say, okay, everything you have is immutable once you create it. And so it's perfectly fine to share it because, of course, nobody else can write to it. Nothing can write to it. Other languages, like if you've worked with threads in C, just say, okay, you've got these things and you can read and write to them. Please try to coordinate among yourselves and decide when you're allowed to do that reading and writing. And so you have things like mutexes, or if you're in Java, you have synchronized methods or something like that. But effectively, there's nothing that really says, okay, one of you can read and write to this and nobody else can read and write to it. Pony actually enforces that at compile time. And again, the thing that it uses to do that is reference capabilities. So in Pony, garbage collection happens between handling messages. It happens at the actor level, and one actor can garbage collect independently of other actors. So if you'll remember when we talked about tracing for garbage collecting, we said that you needed to stop all of your threads if you had multiple threads that could modify the object graph, because you needed to make sure that there weren't other threads modifying the graph while you were trying to trace it. Pony gets around that, and part of the reason it can get around that is with reference capabilities. So like we said, the only actor, if any actor can write to it, then it's the actor that's currently referencing that object. So if an actor is in the process of garbage collecting, it knows that no other actor can modify that object to make it point to something else. And so you never have to worry about the object graph changing. Or if other actors do have access to it, that means that effectively it's a read-only object. And so again, you don't have to worry that other actors are modifying the graph. In between handling messages, an actor is stable. The only way that you can update a actor is by sending it a message and having it process that message. So as long as an actor doesn't have a message that is processing, it doesn't need to worry about being mutated. So let's talk a little bit about collecting actors. So an actor is dead if it is no longer referenced by another actor that can send it a message transitively, which means that it is not referenced by an actor that can send it a message, and that actor is not referenced by an actor that can send it a message, and so on back to the beginning. And the other criteria for it being dead is that it has no messages in its message queue, and we call that state blocked. So again, remember, actors can only respond to messages, and also remember that actors are able to send themselves messages. It's not just sending other actors messages. So an actor can get a message, and when it's processing it, it can reach a point in code where it needs to send itself a message, and it will do that, and that places the new message on its message queue, and it will eventually get to the point where it processes that new message. So you can kind of create a loop there by just sending yourself a message and processing it repeatedly. So there's a thing called the cycle detector, and it's an actor that gets started up as part of the runtime, and it's always running. And it monitors the relationship between actors and determines when they are dead. So when an actor has no more messages to process, it sends a block message to the cycle detector with a list of the actors that it references. So down here we have kind of this graph of objects, A1, A2, A3, and A4. And A1 is blocked, so it sends a block message to the cycle detector. And the cycle detector uses that message to start creating a graph, its own view of the actor graph. And in the meantime, actors A2, A3, and A4 have also sent blocked messages to the cycle detector because they are also blocked. So the cycle detector goes through the messages and processes them and starts creating its own view of what the graph of actors looks like and which ones may or may not be blocked. So it's processing these messages, updating its own view of the system. And finally, it reaches this view where it says, okay, A1 points to A2 and A3, A2 points to A4, and all of these things are blocked. If the cycle detector receives a block message from an actor and its view shows that the actor has no more incoming references, then the actor can be collected. So if you look at actor A is blocked and it doesn't have any incoming references. Nothing points to A1. And so it's blocked, nothing points to it. So it's dead. So A1 can be collected and the cycle detector updates its view of the world. If an object has been blocked, but then it receives a message to process, it sends the cycle detector an unblocked message. So this is the way to update the cycle detector's view and say, okay, I had been blocked, but I'm no longer blocked. So in this case, A2 gets a message, and it starts processing that message, and it sends an unblocked message to the cycle detector. The cycle detector processes that message, and it says, okay, A2 is no longer blocked. So we'll get to it in a minute, but effectively, this lets the cycle detector figure out, okay, what's blocked and what might or might not have other references to it. If the cycle detector believes it has found a cycle in blocked actors, it will attempt to confirm that the actors in that cycle are all blocked by sending conf messages to all the actors and waiting for act messages from them. So remember how we talked a little bit about cycles in reference counting and tracing. So the cycle detector is maintaining its own view of the world, and it eventually gets to a point where it decides that everything has been blocked because all of these actors have sent it blocked messages. So it processes that, processes the next one, processes the third one. And so now it has what we call a perceived cycle. And so it's actually a cycle. These actors only point to each other. But it's not sure if they're dead or not yet. it's gotten messages from each of them saying that they're blocked, but it's possible that that something sent a message to another actor, that one of the actors in the cycle sent a message to another actor, and they may not actually all be dead. So first, let's talk about conf. So the cycle detector sends conf messages to all the actors to confirm or not confirm that they are blocked. So in this case, nothing has any other messages. So all the actors process that conf message, and they send an ACK back to the cycle detector to let it know that they have received the conf message. If the cycle detector receives ACK messages from all of the actors and doesn't receive any other types of messages from them, then it assumes that they are, in fact, truly blocked. And if it determines that all of the actors in the cycle are, in fact, truly blocked, then it's a confirmed cycle. And if you have a confirmed cycle, then you can collect all of the actors in that cycle. But what if at some point along the line, A3 sent a message to A1 before it sent its block message? So let's say that A3 had been processing a message, and when it was done, it sent a block to the cycle detector, but A1 and A2 had already sent their block messages. So A3 sends the message to A1, then it sends a block message to the cycle detector. And so now we have a perceived cycle. But in this case, A1 has a message in its queue, so it's not dead. But the cycle detector doesn't really have a way of knowing that directly. So again, it sends out conf messages. Meanwhile, A1 processes the message that it received from A3, and it sends an unblocked message to the cycle detector. When the cycle detector processes that message, it clears the block setting on that actor, and it realizes that, okay, we may have a cycle here, but our cycle is not blocked. At this point, A1 can still send an ACK, but because the cycle detector knows that it is not a blocked cycle, it doesn't try to collect all the actors. So let's talk about collecting objects next. So there's some important things to know about objects within the context of Pony. An object is owned by the actor that created it. And the other thing to keep in mind is that the actor that owns an object is responsible for collecting it. Now, there's a difference between ownership and reference. We've talked about reference, and we're now talking about ownership here. So objects can be shared between multiple actors or passed around from one actor to another, but the owner always stays the same. So the owner is always the actor that created the object, even if that actor gives up a reference to that object, and the object is only referred to by other actors. So it's possible for an object's owner to not have a reference to it. And again, remember that reference capabilities control what actors can do with references they have to objects. So internally, actors have a heap, which stores references to all reachable objects, all the objects that actor can reach, and all the owners of those objects. It has a queue, which stores messages that have been sent to the actor. We discussed that already. And it has two reference counts. It has a local reference count, which is for each object that it owns. And the local reference count is a map from the objects that it owns to the count of external references to that object. So other actors that refer to that object. There's also a foreign reference count. And that is a map of objects that it does not own to the number of references that this actor holds to that object. So the local reference count is how many of the objects that this actor owns, or how many references are there to different objects that this actor owns from other objects. And the local foreign reference count is how many objects that are owned by other actors do I have? How many references do I have to those objects? So when we're collecting objects, we need to be aware of the fact that there are increment and decrement messages. And these messages are sent between actors. The increment messages are sent when an actor obtains a reference to an object, and decrement messages are sent when an actor gives up or confirms that it no longer has a reference to an object. So the garbage collection algorithm for objects looks like this. The first thing you do, an actor, when it's ready to garbage collect, says, okay, all of the objects that I own are marked as unreachable. Second thing that it does is, for all unowned objects with a foreign reference count of greater than 0, mark those as unreachable. So remember, the foreign reference count is the count of how many times, basically that indicates that an object is not owned by the actor, but it's referred to by the actor. After that, tracing occurs from the actor's fields only, and we mark all the reachable objects, whether they're owned or not. The fourth step is that all owned objects with a local reference count greater than 0 are marked as reachable. So even if they weren't reachable from the actor's fields, if the local reference count is greater than 0, they're reachable. And so remember, the local reference count is the number of references from other actors to that object. Finally, an unreachable owned objects are collected. So remember, actors only collect their own objects. They don't try to collect objects from other actors. And then the final step is that decrement messages are sent for unowned objects that are unreachable, and their foreign reference count is set to 0. So this means that if an actor has determined that some object that it used to be able to reference is no longer referenceable, then it sends a message to the actor that owns that object to say, hey, you've got one less reference than you thought you did before. So I'm going to walk through an example of this, and this example is actually pretty similar to one that's in the paper Ownership and Reference Counting Based Garbage Collection in the Actor World, which is the paper that describes the pony garbage collector. So we've got Actor 1. Actor 1 has objects 01, 02, 04, and 07. So down here we've got local reference counts and foreign reference counts, and they should all correspond, if you count the references between these things, to basically what you'd expect. Same thing with Actor 2. Actor 2 has 03, 05, and 08, and it has its local and foreign reference counts as well. And A3 has object 06. So keep in mind here a few things here. One is that actors A2 and A3 own objects, but they don't have any references to those objects. And also notice that 01, 02, and 03 form a cycle, and that cycle crosses boundaries from A1 to A2 and back again. So let's go through the example. So the first thing we're going to do is we're going to collect Actor 3. We're going to run the GC on Actor 3. So the first thing it does is it marks all owned objects as unreachable. So it owns 06, and it marks it as unreachable, which I've signified with red there. All unowned objects with a foreign reference count greater than 0 are marked as unreachable. So it has a foreign reference count. It has a foreign reference count for 05 of 1. So it also marks 05 as unreachable. Then we trace from the actor's fields marking objects as reachable. So the actor doesn't have any fields that reference 06, and so there's nothing to mark here. All owned objects with a local reference count of greater than 0 are marked as reachable. So we don't have any local reference counts here, which means that effectively 06 has a local reference count of 0, so it's not marked reachable. Once we get to that point, all unreachable owned objects are collected. So for A3, 06 is still unreachable, and so it collects 06. It then sends a decrement message for object 05, because 05 was marked as unreachable, and it's owned by A2. So A3 sends a message dec 05 to A2. When A2 receives that message to process, it decrements its local reference count to 5. Oh, I seem to have made a mistake here. Hopefully that's corrected later on. Well, pretend like that local reference count to 05 is 0 here. Okay, now we're going to collect A2. So for A2, all owned objects are marked as unreachable. Again, same algorithm. So it marks 03, 05, and 08 as unreachable. Oh, I'm sorry. I see what I did wrong here. Yeah, actually, I think when I created the slides, I screwed up. 05 should have started out with a local reference count of 2 because it's referenced from 04 and it was referenced by 06. Sorry. So moving forward with A2, 05's reference count is now correct. Okay, sorry. So we mark all of the owned objects as unreachable. All unowned objects with a foreign reference count greater than 0 are marked as unreachable. So if you look at the foreign reference counts in A2, it has a foreign reference count for 01 and also for 07. Then we trace from the actors fields, marking objects as reachable. So again, A2 doesn't have any references to any of the objects that it owns, so it doesn't mark anything as reachable. Fourth step, all owned objects with a local reference count greater than 0 are marked as reachable. So it looks at the local reference count and it says, oh, well, local reference count for 03, 05, and 08 are all greater than 0. So they must be referenced from somewhere. So they must be reachable from somewhere. They're not reachable from A2, but somewhere else there must be something that can reach them. And then unreachable owned objects are collected. So at this point, as far as A2 is concerned, 03, 05, and 08 are reachable from somewhere. So it doesn't have anything to collect. And then decrement messages are sent for unowned objects that are unreachable. And their foreign reference counts are set to 0. So it can't reach 01 and 02. They're marked as unreachable. And so it sends decrement counts. It decrements 01 and 07. And it also updates its own foreign reference count to 01 and 07. So now A1 eventually gets that message, and it modifies its local reference counts for 01 and 07 and sets them to 0. Okay, now we're going to collect A1. So again, same process. All owned objects are marked as unreachable. So 01, 02, 04, and 07. All unowned objects with a foreign reference count of greater than 0 are marked as unreachable. So 03, 05, and 08. And now we trace from the actors fields, marking objects as reachable. So unlike with A2 and A3, A1 does have a reference to at least one of its fields, or to one of its objects, and that object is 01. And so we mark 01 as reachable, and we mark any object that you can get to from 01 as reachable as well. So that includes 03, because you can reach 03 from 01 by going through 02. All owned objects with a local reference count of greater than 0 are marked as reachable. So we don't have any owned objects with a local reference count of greater than 0. So that doesn't mean that we change the status of 01. It just means that we don't mark it as, we just leave it as reachable. Unreachable owned objects, again, are collected. So we collect 04 and 07. And now we no longer have references to 05 and 08. Those are marked as unreachable, so we send a decrement message to A2. A2 processes that, and it changes its foreign reference counts, local reference counts appropriately. So now we're left in this state. So as you can see, we've been going through here and we've been getting rid of objects. At some later time, A2 is going to collect again. Now we do the same thing, mark all owned objects as unreachable. All unowned objects with a foreign reference count greater than 0 are marked as unreachable. Trace from actors fields marking objects reachable. Oh, I seem to have this out of order. Okay. Basically, 01 should become reachable. And all objects with a local reference count of greater than 0 are reachable. So 03 is reachable. We collect the unreachable owned objects, 05 and 08, and we send a decrement message for unowned objects that are unreachable, and their foreign reference counts are set to 0. So we don't need to do anything there. And so now we're left with the objects that are reachable. So A3 doesn't have any reachable objects. It's kind of living on its own there. A2 still has owns object O3, and because that's part of the cycle of objects here, it remains alive. But all the other unreachable objects have now been collected. And so, again, as you can see, this is kind of one of those hybrid garbage collection algorithms where objects have references to each other, and so those references are traced at certain points in the algorithm. But the actors also maintain counts to different objects, and those are also used as part of the job of keeping track of garbage collection. No? So that kind of concludes what I wanted to talk about in terms of garbage collection in Pony. There's a few places you can look to learn more about how garbage collection works. One of the best places is to start digging into the source code. The garbage collection logic lives in this GC directory within the Pony source code. So if you go to source lib pony rt GC, you'll find these classes, and you should find, should be pretty straightforward to find most of the things that we've talked about in the code. So for example, you see the cycle.c, that is the cycle detector. The other good resource are the two papers, ownership and reference counting based garbage collection in the actor world, and fully concurrent garbage collection of actors on mini-core machines. Sylvan, the creator of Pony, is lead author on both of those papers, and both of those papers are available on ponylang.org. And you should be able to go there to learn a little bit more about some of the details of how the garbage collection system works. That second paper actually has a lot of proofs as well, so you can see that the actor garbage collector is formally verified. So that's it. And thank you for sitting through my talk. And are there any questions?
Well, if no one else is going to jump in, I'll jump in.
Okay.
Can you? Thank you very much. I thought that was really well put together. Can you tell me sort of what it is that motivated you to learn in such detail how the garbage collector actually works?
Sure. I've always kind of been interested in how garbage collectors work. I've done talks in the past about garbage collectors, and so it's kind of a hobby of mine. And so I wanted to kind of see what made Pony tick. The other part of it is that we use Pony here at the company that I work for, Sindence. And occasionally we will see behavior with a garbage collector that we want to explain. You know, something will happen maybe that's a little unexpected, or we'll want to predict how the garbage collector is going to behave in certain circumstances. And so I've spent some time digging into the garbage collector code along with Sean Allen, and certainly under the tutelage of Sylvan. And so that's kind of how I've gotten to this point.
Excellent, thanks.
Yep. Anything else? Okay, great. Well, again, thank you very much for showing up. And if you're watching this talk later on, thank you very much for watching this talk, and have a good night.